So we'll be taking you through number theory and cryptography. We have 5 subtopics to discuss. The first one is Fermat's theorem, the check digits, multiplicative inverse, linear congruences, and affine ciphers. So I'll be taking you through the Fermat's theorem, and here's a little bit of introduction. Fermat's theorem helps us to calculate the power of modulo n when n is a prime number, and its main application, it's used in RSA ciphers, which is widely used for disguising sensitive information. For that, I will be showing you one example of how to tackle a Fermat's question when you find one. So suppose you're presented with such an equation and you're told to find the least residual of such. So what you do, the first step is you take 25, you find its module of 6, of which it will be 1 because 6 goes 4 times in 25, goes 4 times to make 24, and the remainder is 1. So that becomes 25 power 25 modular congruent. It's congruent to 1 power 25 modular 6. That makes it the least residual of 25 power 25 modular 6 is 1. That is when you're given a number that is positive. For an event that the number is negative, like negative 9 power 4 modular 6. So what you do, you divide negative 9 with 6. At this point, using a number line, negative 6, negative 9, negative 10, 11, 12, 13. In such a number line, negative 9 will divide 6 2 times to make it 12, but the remainder will be 1, 2, 3. So it will be negative 9 power 4, which will be congruent to 3 power 4 modular 6. At this point, we can see that the least amount of residue for negative 9 power 4 modular 6 is 3. There is another unique event where it's called Carmichael number, and this is where now the power number, it's not prime and it's an even number, but all this happens only in special occasions for numbers like 561, 1105, and 1729. The other numbers are large, and we wouldn't be focusing on them right now. And that is it for the Fermat's theorem.
Hi, I'm Faith. I'll be taking you through through check digits. So basically, check digit is the last number that is always on a barcode. A barcode is this number. This is a barcode. So this last digit here, like this one, Sasa, the 3 here, is always is known as the check digit. A barcode is divided into 2. A universal product code, which is normally in any product that is in the US, in the UK, and then there's a international standard book code or number which is in any form of book, the code in a book. In this section, we're gonna learn how to work or find if the barcodes or the numbers in the barcodes, the ISBNs, are correct or valid and how they work. So we're gonna take an example of a book, and we're gonna take the barcode behind the book, and then we're gonna illustrate how we're gonna find whether the code is correct, the code is valid to be an ISBN. You take the code of a book called Silent Spring by Rachel Carson. This is the barcode, the code behind that book. We put it in reverse. We put the number in reverse order so that A1 is the check digit. So the number is gonna be, we're gonna start with the 0. So it's 0 1 4 1 3 9 1 5 2 9. Then we're gonna have this number as the check digit. This is the check digit in this code. We're gonna label these numbers from A10. Okay, from A1, starting from where the check digit is. This is gonna be A1, and then we go in reverse. A1, A2. It's A2 to A10. The numbers represent the language, the publisher, the title of the book, and then there is this number, the A1, which is the check digit. So the check digit A1 is then defined to be is an integer. The A1 is mostly always an integer from 0 to 10. A1 is A1 satisfies the following. We're gonna write it down here. Now we're gonna put this out like so. Unaona tushai label hapa A1, A2 up to A10. So we're gonna put it like an equation. Okay. Pause. Niandike. For our code to be considered a valid ICBN, it must satisfy these congruence. So let's check if the Silent Spring book code satisfies these congruence. If it satisfies the congruence, then there's no error, and it's considered a correct ICBN. So we're gonna start. Our A1 was 9, so it's gonna be 9 plus 2A by 2. So our 2, we take the 2, we multiply by the A2. The A2 in this situation is a 2. Yeah. Added by the A3, which is A, multiplied by the A3, which is a 5. And then the 4. We continue with all the other numbers. We simply simplify the above by multiplying the numbers out, and then we add them together. From what I took from the examples given, we're gonna simply take the numbers that are more than our module, which is 15, 45, 18, 32, and divide them by the module, and then we're gonna take the remainders, the residue. We're gonna take the remainders. Okay. 0 divided by a number is simply 0. When we add all these, we get 55. So 55, when you 55 is divided by the modulo, the remainder, or the residue, is 0, since when you divide 55 divide by 11, you get 5. So the module, the remainder, is 0, making our statement mod 11. This means, we can simply say, our book, the silent spring barcode, marks or checks to be a correct ICBN and cannot produce or generate any errors. The most common errors that occur when communicating ICBN are mostly interchanging the adjacent digits when you're typing or putting in the code, or uttering a digit. For example, if it's a number 6 and 5, you get to interchange the 5 and 6, which brings out a really different code. Or if you alter a single digit, for example, a code had a 9, and then you end up putting a 3 in the spot of a 9, that generates an error. To consider an ISBN code valid, it has to satisfy the congruence check, which is mostly the number should be congruent to 0 mod 11. If it satisfies the congruence, then it's a valid ISBN.
And I'll be taking us through multiplicative inverse. So multiplicative inverse in an operation is the inverse of an integer that when it is multiplied, we get a result as one other result. So for instance, the inverse of 5 is 1 over 5. Why is this? 5 multiplied by that a fifth, we get an answer as 1. Given some work samples to be done, let's say under mod n, we are given maybe a summation like a multiplied by the inverse of a congruent 1 mod n. So we're given samples like 3 multiplied by an unknown number congruent 1 mod 5. So for us to get this unknown number, the inverse of 3, we multiplied this, the 3 multiplied by the unknown number, we should get, and divided by 1, we get 1 as an answer. So let's start from 1. 3 multiplied by 1, we get 3. 3 divided by 5, we don't get 1 as an answer. So we move to the next. 3 multiplied by 2, we get 6. 6 divided by 5, we get 1. We get 1 as an answer. So for us to satisfy this equation, we take it as 3 multiplied by 2, which is the multiplicative inverse of 3, congruent 1 mod 5. So when we take 3 multiplied by 2, we get 6 divided by 5, we get 1 as mod. Let us go to the next summation, get 1 as the remainder. So let us move to the next summation. 2 multiplied by an unknown number congruent 1 mod 11. So what number can we multiply by 2 and divided by 11 to get a remainder of 1? So let us start from 1. 2 multiplied by 1, we get 2. 2 divided by multiplied by 1 divided by 11, we don't get 1 as an answer. So let us move to the next number, which is 2 multiplied by 2. It is 4. 4 divided by 11, we don't get 1 as an answer. So for this case, 2 multiplied by 6, congruent remainder 1 mod 11. So 2 multiplied by 6, we get 12. 12 divided by 11, we get 1 as a remainder. So that is how it is. Case, what's any example? So let us have an example with a number that. So another case, in the case of 5 multiplied by an unknown number congruent 1 mod 10. So if we take a number which is unknown, multiply it by 5, and we divide it by 10, we shall get a remainder of 10. So in this case, let us start by 5 multiplied by 4 congruent remainder 1 mod 10. So 5 multiplied by 4, we get 20. 20 divided by 10, we get an even result, which is 2 and not 1. So in this case, there is no remainder. So in this case, this equation doesn't satisfy the multiplicative inverse. So using the Euclid's equation for the case of big numbers, so we have the quotient, then A, B, remainder, T1, T2, and T and T. So things to note. First, A is always this A is always greater than B. And number 2, T1 is equals to 0. This T1 is always 0, and T2 is always equals to 1. This T2 is always equals to 1. So, and T equals to T1 minus T2 multiplied by the quotient here. So for us to get T1 is T1 multiplied by T2, and T1, you negate T2 multiplied by the quotient, we get this T. So for example, we are given find the multiplicative inverse of 3 and 5 using the Euclid's equation. So for this case, we use the formula remainder B and Q. So from the notation here, the note A is always greater than B. So we take this 5 and input it here at 5 at A and B 3. So using this equation, we input 5 here, and then B is 3, and then 5 divided by 3, we get a remainder of 2, and then the quotient is 1. So for this case, quotient is 1, remainder is 2. So for us to calculate the values of T1, always from this note, T1 is 0 and T2 is 1. So for us to calculate the value of T, we take T is equals to T1 minus T2 multiplied by the quotient, which is 1. So T equals to T1, which is 0, minus T2, which is 1, T2, which is 1, multiplied by the quotient, which is 1. So the answer is 0 minus 1, that is negative 1. Negative 1 multiplied by 1, we get the value of T as negative 1. So we get the value of T as negative 1. So for this case, we change. For us to continue with the equation, we move the value of B to this place, which will be 3, and the value of R, we move it back to this where B is, which is 2, and then we do the same for T1. For T1, we are adding this 2. So we move this value, this value here to 1, and this other value as negative 1. So we continue with the same process of finding the value of T until there is no more so you continue the same process as in here until you get the quotient as 1.
My name is Samuel Mbuvi. I'll be taking you through linear congruences. So a linear congruence is an equation in the form of ax congruent b mod m, where a, b, and m are integers and x is an unknown integer variable, and this is the congruence symbol, which means that the two sides of the equation have the same remainder when divided by m. Solving a linear congruence involves finding all possible solutions for x that satisfy the equation. There are a few steps to solve a linear congruence. First, it involves finding the GCD. Finding the GCD is a necessary condition for solving the equation because the GCD determines if the equation has a solution. The GCD is found by, the values that are used to find the GCD are A and M. The GCD of A and M should be able to divide B. If the GCD of A and M can divide B, then it means there is a solution. But if the GCD of A and M cannot divide B, it means there is no solution. For example, the GCD of A and M should be able to divide B. Let's say the GCD is D. D should be able to divide B. Now this value. Let's start with a solution, a case where there is no solution, which is an unsolvable case. For example, let's take 2x congruence 51 mod 8. So the values, this is value A, value B, value M. The GCD, the values we used to find the GCD at value A and M, so we take the GCD of 2 and 8, which is 2. So 2 should be able to divide 51, but in this case 2 cannot divide 51, which means there is no solution in this case, which means this congruence is unsolvable. We can't solve it, so we move on to the next case. Case number 2 is the case where there is only one solution for the congruence. Let's say, for example, 4x congruent 26 mod 7. When we find the GCD of 4 and 7, GCD of 4 and 7, the GCD is 1, which means that 1 divides 26 only one time, which means there's only one solution. So we can go ahead and find the solution. We say 4x congruent 26 mod 7. We can simplify this equation. We take these values A and B, we divide them by 2 so that it can be, we divide them by 2. So we get 2x congruence, this is 13 mod 7. You notice here we have not divided this mod 7. So at this point you ask yourself if you can add or subtract multiples of 7 to 13. We can create what is it called? A list residue system. Let's say we start with 13 plus 7 we get 20, plus 7 we get 27. On the other side we get 13 minus 7 we get 6, we get minus 1. So in this case we're supposed to find a number here which is divisible by 2 and closer to 0, which is 6 is the closest number to 0, which is divisible by 2. So we substitute this 13 with 6 to get the equation, which is 2x congruent 6 mod 7. When we simplify, we divide by 2, we get x congruent 3 mod 7, and this is our solution to this linear congruence. In case number 3, we have the linear congruence with multiple solution. Let's take, for example, 9x congruence 42 mod 6. First we find the GCD of A and M, and the GCD is 3. The GCD for 9 and 6 is 3. So when you divide 3 by 42, 3 can divide 42. But the GCD is the number of solutions, which means there are 3 solutions for this linear congruence. 3 solutions. So we go ahead and calculate how we did in the previous equation. Pause. In this case, we can simplify this by 3, so we can divide it by 3. But in this case, we can also divide the whole equation by 3. So it can be 3x congruent 14 mod 2. So we can let the least residue system of 14, starting by 14. When we add 2, we get 16, but we are looking for a number that is closer to 0. So we go back and say 12, 10, 8, 6, 4, 2, 0. So we take a number that is closer to 0 that is divisible by 3, which is 6. We substitute 14 with 6. After listing down the least residue system, we take a number that is closest to 0, and in this case, when there is a 0, you can opt to take for the 0. So we substitute the 14 with 0, and we get a new equation which is 3x congruent 0 mod 2. So when we simplify it, it will be x is congruent to 0 mod 2. So let's not forget we had 3 solutions in this case. So which can be written, solutions can be written in the form of x congruence b. This is mod 2. So we write mod 2. No, in this case it was mod 6 originally, so we write mod 6. So we can substitute, we can write an equation which is 2t plus 0. So this b is equals to 2t plus 0, where t are values in a table. We can draw the table in here. We say t, and this is b. Okay, so we start the values from 0, 1, 2, because there are 3 solutions, so it is 1, 2, 3 solutions. So we substitute t with 0, we get 2 times 0 plus 0 is 0, 1, 2 times 1 plus 0 is 1, and 2 times 2, 4 plus 0 is 4. So in this equation we will have the equations in this form. We say the first equation, the first solution is x is equals, so we say x is equals to the first number we get, 0 mod 6. So this was the first solution. The second solution is x congruent 1 mod 6. And the third solution is x congruent 4 mod 6. Yes, and that is it, guys.
That's the solution.
These are the solutions.
I'm back and I'll be taking you through affine ciphers. So affine cipher, let's just say, okay, ciphering, it's the use of an algorithm that is used to transform a message or to encrypt a message, and this process of ciphering is called cryptography. So here we have a table that runs from letter A to letter Z, and below it we have numbers, like number 0 through to 25. So what we'll be doing in this topic, unaweza hit pause. So an affine cipher modulo of 26 is a rule of E. E is for the enciphering, and it's used to reorder the integers. So to misema, we've said that from letter A to Z is represented by integer 0 to 26. So for this, we have a formula that E into bracket x is concurrent to ax plus b modulo 26. Here, where A, not this one, and b are integers, and A and 26, not this, A and 26, they are coprimes. You have encountered this coprime in the multiplicative inverse, yes. So for a different set of characters, now you'll just exchange the modular 26, you replace it with modular n, but the rule remains. For these integers A and 26 are coprime. They are coprime, so that A has a multiplicative inverse of modulo 26 that we've seen. We're going to take an example. As you can see, I have a worked out example of x concurrent to 3x plus 14 modulo 26, and we want to encipher the message brouhaha. So for that, we'll just draw a table representing the alphabets and the numbers. And for this, you can see that B, it's number 1, R is number 17, 0 is number 14. So you go indicating here below, and you remember to put commas so that you can differentiate the numbers. After this, you can either do it this way, or you can actually apply the affine cipher rule. The affine cipher rule, it's the formula that we had encountered before. So for this, we will substitute the letters of brouhaha, their numbers now. And for that, E1 for the letter B will be concurrent to 3 into brackets 1 plus 14, which will be concurrent to 17 modulus 26. And that will follow for every other letter. The number 17 for the letter R, number 14 for the letter O, and so on and so forth. And for this, at the end of it, it will be 17 and 13, 4, 22, 9, and 14. So yeah, that's it. So you remember, first step, you have to encipher using the table of alphabets, and then the numbers that you'll get, you run them through the formula, and at the result will give you now the affine ciphered message. After that, after enciphering, there is deciphering. If we have a positive, we have a negative of everything. So for this, it's a process of recovering an original message from an enciphered message. Okay, so for that, suppose we have a message which is 6, 19, 0 and 0, 23, 2, 23, 0, 15 and 15. And it's created by an affine cipher E, x concurrent 5x plus 23 modular 26. So for this, you'll first solve the congruence. Okay, so for this, we'll first solve the congruence. The congruent part of this, so 5x plus 23 is congruent to 6 modular 26. To find x, we subtract 23 from both sides. So from this side, we subtract 23, and from this side too. That will result to 6 minus 23, which will be congruent to negative 17. And negative 17, when you run a modulo of 26, will be congruent to 9 modulo 26. So you obtain 5x of this other part, 5x congruent 9 modulo 17. You realize now this equation, this part, is a linear congruence that we had encountered before. Since this 5 and this 26, they are coprimes, and the solution is x congruent to 9v modulo 26. For this part v, the v that we have introduced is a multiplicative inverse of 5 modulus 26. Like we had encountered before in multiplicative inverse in the linear congruence. Yes. So 5 times 5 is congruent to 25, which is congruent to negative 1 modulus 26. This, when you work it out, it gives you negative 5 multiplied by 5, which is congruent to 1 modulus 26. Hence 5 is the multiplicative inverse of 5, like we had encountered before. So instead of going through all that, we have a deciphering rule that is an inverse of the enciphering rule that we had before. So for this rule, it's dy, which is congruent to v into brackets y minus b modulus 26, where we've said that v is the multiplicative inverse of modulus 26. We have an example here that we're gonna run with. So we have a message that is 3, 17, 18, and 7, and its affine cipher is e into bracket x congruent to 9x plus 21 modulus 26. The deciphering of this dictates us to substitute the b with 21. This one, we drop it, 21, and modulus stays. V being the multiplicative inverse of 9 and 26. This 9 and this 26. They have to be coprimes for them to be multiplicative inverse. So you notice that when you multiply 3 and 29, it gives you 27. And for this case, the modulo of 26 gives you a remainder, a residue of 1. So instead of going through the Euclid's algorithm to just cut the time, you'll just multiply, you'll just have 3 multiplied by 9 congruent to 27, which is congruent to 1 modulus of 26. So 3 here is a multiplicative inverse of 9 modulo 26, like I've explained. So for this, when after you've worked at that part, you run the formula. So we'll be substituting every digit of the message to the letters that we have. So for the first letter of the message, it was 3. So 3 goes into the place of y, gives you a congruent of 3 into brackets 3 plus 5, which is a congruent of 24 modulus 26. That applies to the rest of the message, 17, 18, and 7. And at the end of it all, you have the letters, the message 24, 14, 17, and 10. When you run this message through the table, you'll find that 24 is Y, letter Y, 14 is letter O, 17 is letter R, and 10 is letter K, and that gives you the word deoxo. The deciphering method, the deciphering rules, and everything has brought us to the conclusion that the message was York, and that is the affine ciphering.
So I'll be taking us through activity 38, deciphering messages that have been enciphered using affine ciphers. So suppose you receive two messages that have been enciphered using the specified cipher A. What do the messages say? So for example, for part A, we were given this message which has 14, 10, 6, 22, 22, using A as an affine cipher, congruence 5x plus 10 modulus 26. So for this rule, a rule D for deciphering the message is given by D into Y congruence V into Y minus 10 modulus 26, where V is a multiplicative inverse of 5 modulo 26. Since the 5, this 5 multiplied by 5 congruence 25 is equals to 1 mod 26. So we take these values here and input them into the rule, the deciphering rule. We see that negative 5 is a multiplicative inverse of 5 modulo 26. So D into Y congruence negative 5 into Y minus 10 modulo 26, hence D, we take the first 14 here, and negative 5 into 14 minus 10 congruence negative 20, 6 modulo 26. So for the second part is D into 10 congruence negative 5, 10 minus 10 congruence 0 modulus 26. Then we go to the third part, which is D 6 into 6 congruence negative 5 into 6 minus 10 congruence 20 into modulo 26. Then the last part, which is 22, D into 22 congruence negative 5 22 minus into 22 minus 10 congruence negative 6, which is equal to 18 modulo 26. So the deciphered message is 6, then this 0, then 20, and 18 for part of 22. So using this same table, the 6 goes to G, and then 0 goes to A, and then 20, the 20 is U, and then 18 is SS. So the deciphered message is this. But we roll D for deciphering the message is given by D into Y congruence V Y minus 6 mod 26, where V is a multiplicative inverse of negative 9 modulo 26, since negative 3 multiplied by negative 9 congruence 27 congruence 1 modulus 26, we see that negative 3 is multiplicative inverse of negative 9 modulo 26. So d into y congruence negative 3 into y minus 6 modulus 26, hence we take the first number, which is 22, d into that 22 congruence negative 3 into 22 minus 6 congruence negative 48 into congruence 4 mod 26. Then the second number, which is d into 8 congruence negative 3 into 8 minus 6 congruence negative 6 congruence 20 modulus 26. Then d into 11, the third value, congruence negative 3 into 11 negative 6 congruence negative 15 congruence 11 mod 26. Then the last bit, d into 9 congruence negative 3 into 9 minus 6 congruence negative 9 modulus negative 9 congruence 17 modulus 26. So the deciphered message is this 4, 20, 11 and 17. So is 4, 20, 11, and 17, which when using the table A, B, C, D, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Five. So the numbers, which is 4, is E, and then 20 is U, and then 11 is L, and then 17. 17 is 17 is R.